Good morning all. Myself Balaji from INCOIS. I'm going to present about impact of assimilation on ocean state estimation, mainly with assimilation of remote sensing data, that is GHRSST data. Ocean state forecast is extremely important for a wide spectrum of individuals and offshore industries. For this purpose, ocean general circulation models are used. At INCOIS, a high-resolution ocean model using ROMS is operational, which provides ocean state forecast for the Indian Ocean domain. To further improve the ocean state, a data assimilation system is developed by interfacing the operational ROMS with LETKF scheme. This data assimilation system assimilates along-track GHRSST data and in-situ temperature and salinity profiles. In this slide, I am presenting about the specifications of the model and the assimilation system. The model used is Regional Ocean Modeling System ROMS, whose domain extends from 30 east to 120 east along east-west direction and 30 south to 30 north along north-south direction. The horizontal resolution is close to 9 km, that is 1/12 of a degree, and the 40 vertical levels are used. As this is a regional model which requires a boundary condition, the boundary condition are obtained from INCOIS GODAS, and the atmospheric fluxes are obtained from NCMOW GFS model. The final ocean products are temperature, salinity, currents, sea surface height, MLD and D20. The assimilation scheme is LETKF, local ensemble transform Kalman filter, with 80 ensemble members. In the context of data assimilation, observations can be classified into two categories, that is, assimilated observations and independent observations. Assimilated observations are those observations which went into the system, whereas independent observations are not assimilated, and these are very helpful while evaluating the performance of the system in ocean state estimation. In the present data assimilation system, the assimilated observations are temperature, salinity and satellite SST. And the independent observations are sea surface height, sea surface currents and sea surface salinity. In the left, I am showing the spatial distribution of in situ assimilated observations, that is temperature and salinity. These are the observations from various observation networks like Argo, moored buoys, ship tracks. In the right panel, I am showing the satellite track data which went into data assimilation system. Block diagram of assimilation system is presented here. This is an ensemble based assimilation system. There are 80 members in this system. All the 80 members run in parallel for 5 days, and on 5th day the observations are assimilated. The specialty of this system is the first 40 members use KPP mixing scheme and remaining 40 members use Miller-Yamada mixing scheme. This is very helpful in maintaining the ensemble spread, which is always a challenging task in any assimilation system. The final product of this is an improved initial condition which serves as analysis and also initial condition for forecast models. Before proceeding to the actual result, I want to highlight the importance and impact of SST assimilation. For this purpose, a sensitivity experiment is carried out for a period of 6 months. First 3 months only temperature and salinity observations are assimilated, and after that SST observations are introduced. The first row shows the observation count, that is number of observations assimilated. The time series of observation count is presented in the first row. On the left hand side, I am showing the time series of correlation and RMSE of sea surface temperature from both the systems. One is free ROMS and another one is LETKF ROMS. Red color is for LETKF ROMS and blue color is free ROMS. Here we can clearly see that with introduction of SST observations, the LETKF ROMS correlation is mostly greater than 0.95 for the entire time period. On the right, I am showing for surface currents. Similar analysis for surface current, and the surface currents are independent variables. The dotted line shows for meridional current and thick line is for zonal current. Here also we can clearly see that with SST assimilation, even the independent variables, the LETKF ROMs is doing good. Model derived SST is validated with AVHRR observations. Here I am showing spatial correlation and spatial RMSD from both the models. The correlation has improved in most of the regions. First row indicates spatial correlation, whereas second row is spatial RMSD. The improvements in correlation are very significant over Arabian Sea and Bay of Bengal. Coming to the RMSD, the LETKF system has reduced significantly RMSE. Especially in North Indian Ocean domain, the reduction is close to 1 degree centigrade. Here I want to highlight the impact of observations. For this purpose, I chose two boxes R1 and R2 and tried to show the time series of observation density over these boxes. Observation density is number of observations by the area of the boxes. So it is clear from the figure 3, R1 is having more observation density compared to R2. This is leading to the improvements in correlation and RMSE over these two regions. Improvements in zonal currents are presented here. Currents are independent variables, means no current observations are assimilated in the present system. First row indicates correlation patterns and the second row indicates spatial RMSD patterns. Figure C highlights the differences in correlation patterns from both systems, that is LETKF minus free ROMs. Red indicates improvement and blue indicates degradations in figure C. LETKF is improving in correlation in most of the regions. The second row is similar analysis for RMSD. Here also LETKF has reduced RMSD in most of the regions, especially in North Indian Ocean and Equatorial Indian Ocean region. The improvements are significant. That is, reduction in RMSE is close to 15 cm per second, whereas the improvements are minimal or negligible in South Indian Ocean. To inspect the reason for this, we have plotted the observation density over the four regions as shown in this figure. Compared to other three regions, that is Arabian Sea, Bay of Bengal, Equatorial Indian Ocean, South Indian Ocean is least observed and having less number of in situ temperature and salinity profiles. Comparison of subsurface currents is presented in this slide. The model derived zonal currents is compared with ADCP observations. LETKF ROMs tries to manage this observed spatio-temporal variability, whereas OROMs is overestimating. The large current system, that is Virki jets, during October-December is captured by both the systems, whereas the intense current persists for a longer period in free ROMs. This overestimation is reduced in LETKF ROMs. Improvements in current estimation is presented in this slide. For this purpose, the meridional currents from Tamil Nadu coast is compared with HF radar observations. First row indicates correlation patterns, second row indicates RMSD patterns. Figure C and figure F highlights the differences in correlation and RMSD respectively. In figure C, red color indicates improvement and figure F, blue color indicates degradation. So LETKF is reducing RMSE and improving correlation over the entire coverage region. Therefore, assimilation of SST has resulted in significant improvements in ocean state estimation. The most profound improvements were seen in currents. These are independent observations and are not assimilated. There is a reduction of 5 cm per second in RMSE over entire domain and 15 cm per second in equatorial Indian Ocean. LETK FROMS has shown better predictability of surface and subsurface currents with assimilation of SST. Thank you.